Okay, dear students, I start the lecture 4 of Math 208. In this lecture, I start with one more new definition, but before that, I just remind you the previous definition. Definition of a linear combination of vectors. U1 and U2 up to UN, these are vectors, and alpha 1, alpha 2 up to alpha n, these are scalars. Then this vector is known as a linear combination of U1, U2 up to UN. Just remind this definition. So up to here you have three definitions. Before I start, you pause this video for a few moments and read three definitions: vector space, subspace, linear combination. So I start with definition of a span of a set S. The span, this is symbol, of a subset S of a vector space V is the set of all finite linear combinations of S or S subset V. Here finite linear combination means U1, U2, UN. You may include this as a finite linear combination, as in the previous definition. Means the number is fixed, 1 to 10, 15, 50, 100, whatever, but it is fixed. We select only finite numbers of elements from S. S may have infinite number of elements. For S subset V, span S is defined like this, where it's a set of all vectors alpha 1 U1, alpha 2 U2, alpha n UN, where alpha is our real numbers and U1, U2, UN belongs to S. Read this definition and then we go further. So students, there is one more theorem. Let S be a non-empty subset of a vector space V. Then span S, the span of S is a subspace of V. Then we want to prove that. Prove that span S is a subspace of V. For that, we have to use the theorem which we have proved in the today's lecture. In the previous lecture, not today's lecture. That is theorem 8. To prove this, span S is a subspace of V, we are going to use theorem number 8. Proof. So read the statement of theorem 8. Pause this video for a moment and go back to previous lecture. here S is not phi. S is subset of V. Let U and V belongs to span of S. Therefore, by theorem 8, it is sufficient to prove that U plus V belongs to span S and alpha U belongs to span S for all scalars alpha. As here U and V belongs to span S, therefore U equal to alpha by U1, alpha to U2, alpha and UN, and V equal to beta 1 V1, beta 2 V2, beta n Vn, where alpha 1, alpha 2, alpha n real numbers, beta U1, U2, UN belongs to S, beta 1, beta 2, beta n belongs to real numbers, and V1, V2, Vn belongs to S. Now what is U plus V? Therefore, U plus V is alpha 1 U1, alpha 2 U2 plus alpha n UN plus beta 1 V1, beta 2 V2, beta n Vn. All these belongs to S. And all alphas and all betas are real numbers. Therefore, this is belongs to span of S. Obviously, therefore, U plus V belongs to span S. And alpha U means we have to multiply this by alpha, means it is alpha 1 U1, alpha 2 U2, alpha n UN. Obviously, this belongs to span S. Therefore, by theorem 8, both the conditions are satisfied, and therefore, span S is a subspace of V, and therefore, this theorem is over, but you have to check for a few moments. So students, everything is on the board. Definition of a span and theorem on a span. So you can understand it very properly. Clear? So dear students, here we start with one more theorem. Theorem number 12. You can see it on the board. The statement of the theorem is that if S is a non-empty subset of a vector space V, then span is the smallest subspace of V containing S. So I suggest you to read this statement at least 3 to 4 times and try to understand the idea what we want to prove actually. So if S is a non-empty subset of a vector space V, then span S is the smallest subspace of V containing S. If this is the smallest subspace which contains S. Here we want to prove that span S is a smallest subspace containing S. For that we have to prove that one, S is subset of span S, and 2, if T is a subspace so dear students, we have to prove these two things. Now, in the previous theorem, this is previous theorem in which we proved S is a subspace. Here we want to prove that S is a non-empty subset of a vector space V, then span S is the smallest subspace of V containing S. This means that S is subset of, first we want to prove that S is subset of S, and if T is a subspace, and S subset T, then span is subset of T. This means that this is V, this is T, and this is S. S is subset of T. Then we want to show that This is span S, and span S contains S. Also, it contained in the span S is subset of T. That we want to show. Clear? This is on different colored chalk we use for span S. Just to understand this, the logic behind it, and then I will do it. So, by the above theorem, we know that span S is a subspace of V. First we want to show that S is subset of span S. To prove S is subset of span S, let uniqueness implies 1 into U is in span S and 1 into U is U. Means whatever U in S it is belongs to span S, and therefore S is subset of span S. Second, let S is subset of T and T is a subspace of V. Let W belongs to spans. Therefore, W equal to alpha 1 U1, alpha 2 U2, alpha and UN, where alpha 1, alpha 2, alpha n are real number and U1, U2, UN belongs to S. But you know that S is subset of T, means U1, U2, UN belongs to T. But T is subspace. Therefore, alpha 1 U1, alpha 2 U2, alpha and UN belongs to T because T is subspace and this is W. So whatever W is in span S, W is in T, and therefore span S is subset of T. Then therefore, span S is a smallest subspace of T of V containing S, and therefore it's close to here. So check this, and with this note I stop this lecture here, but you may check it once more.